I hope you enjoyed your extra sleep this morning. So here's what I want to do today. We talked last time, so we've now got the 3 laws of motion. And then we talked about net forces last time. So we had the dot with the arrows on it, or we had those boxes where we were filling in the missing forces and using that to find the net force. What I want to do today is I want to dig a little bit deeper into that idea of net forces and free body diagrams. So what we're going to do is we're going to take notes, and then I think we're going to have enough time. This is a practice we're going to do, but we're going to do it together. The only thing that I'll say listed down here on with homework is if you would like to do test corrections, those are open now. And I would recommend getting them done before giving so that the information doesn't fail. All right, so let's go ahead and get started. So if you have your notebook out, get out your notebook. If you don't have a notebook, get out a sheet of paper, because we're going to start by taking some notes. And you can label your notes dealing with multiple forces. And this was kind of, we started doing this last time that I saw you, but I want to go into a little bit more depth. And basically, I want to categorize, when I'm talking about forces on an object, I want to categorize all the forces we talk about into 6 types. So there are 6 types of forces. Let's see here. So Scott is here. All right. So I'm just going to go through the 6, and then we'll go through some examples with them. So the first type of force we're going to call the applied force. And the applied force uses the symbol for it is F for force with a subscript of A. Some people say, why is it not AF? Well, just like we had VI and VF for initial velocity and final velocity, we have FA and FT and FF, but in this case, FA means applied force. When I talk about an applied force is any generic push or pull. The next force we're going to have is what I'm going to call tension. And as you can imagine, in terms of what tension is, it's how tightly, how much force a rope exerts. So tension force is a force from a rope or a cord or something like that. The third force is friction, which we're going to abbreviate FF. So friction, like when you rub your hands together, that's an example of friction. But when we talk about the motion of an object, a friction would be something that is trying to oppose the motion. So we're going to say that it's a force between surfaces that opposes motion. Please stop me or put something in the chat if I'm going too fast. All right. Next, we got 3 more forces. The next one is like friction, but we're going to call it air drag or air resistance. And we use the symbol FD for that. And it's like friction in that it opposes motion, but it opposes motion, and it's not due to a surface, it's due to air. So we're going to say a force caused by air that opposes motion. We're almost done. The last two are the easiest, but they're also the most important. So the next one we're going to talk about is weight. Weight is a force. So we can call it weight, or we can call it the force of gravity. And we're going to abbreviate FG. And that's self-explanatory, so I'm not really going to write anything about it. So you know what force of gravity is. It pulls you down. And then the other one that's important, though, is something that we're going to call the normal force, or Fin. So a normal force is going to be, I'm going to write down the definition, and then I'll explain what it is. A normal force is a support force due to friction. So for example, we can think about if you are like standing on the ground, if you stand on the ground, so you have gravity that's pulling you down. That's why you're on the ground. However, you don't fall down because there's a ground there. And so the ground provides a support force pulling you up. We call it the normal force. The reason we call it the normal force is because it's, normal is a mathematical term that means perpendicular. And if you imagine a surface that's flat, if the normal force points up, that's perpendicular to the surface. Okay, now this doesn't really make sense until we actually try this out. So I'm going to change the screen here in a second, but does anyone need this screen still? All right, so we're going to do some example problems. I'm going to do it on a PowerPoint because it's easier for me to see, but you're just going to continue on with your notes to do these in your notes. Oops. So let's go to, let me find the PowerPoint first. So now I'm going to share it with you. All right, so here's the first problem that I want to think about. So we're going to imagine a cat that's sitting at rest on the top of a table. Turn off my video for a second. All right, so we're going to talk about a cat that's at rest on the top of the table. First question, based upon what we talked about last time, is this cat in mechanical equilibrium? And I'm going to have you in the chat tell me what you think. Is the cat in mechanical equilibrium if he's sitting at rest? So go ahead and just put an answer in the chat, yes or no. Is the cat at mechanical equilibrium? I think I agree. It is. So Max says it is in mechanical equilibrium. And yes, because remember, mechanical equilibrium means that your net force is 0, which makes sense if you're at rest. Okay, good. All right, so here's what we're going to do. So the first thing that you would write, so if you just want to write in your notebook, example problem 1. So the answer to A is yes, it's at rest. So it is in mechanical equilibrium. So now what we're going to do is we're going to draw the free body diagram. So a free body diagram, this is the new thing, but we're going to use those forces that we just talked about, okay? So let me see here. Go away. All right, so why am I not? For some reason, it's not letting me write. Probably need another battery. Give me 1 second here. right, let's try this again. When I draw a free body diagram is always going to start with a dot. And again, you kind of saw something like this yesterday. But we're always going to start our free body diagram with a dot. And then of those 6 types of forces that we put on our, that we wrote down in our notes, we're going to think about which forces are acting on the cat. All right, so in the chat, just give me an example of those 6 types of forces, what's a force that you think applies in this case for a cat sitting on a table? Right, we've got applied, tension, friction, air drag, weight, normal force. Which of those do you think might apply to cat on the table? Weight would be a good one to start with, right? So what we're going to do is we know gravity pulls us down, right? So I'm going to start by drawing all of our forces. We want to start from the dot and go out of the dot. So I'm going to draw weight going down, and we label weight as FG, right? So I've got weight going down, but we said we're at mechanical equilibrium. So if we're at mechanical equilibrium, that means that we have to have some other force that's canceling out the weight. So it's sitting on a table. In other words, it's sitting on a surface and it's being supported by a surface. So what force would that be? So we could say that there's an applied force, but generally I would say that an applied force, so what you're calling generic, Danny, so an applied force would be like if I'm pushing something, and we'll give an example of that in a second. Resistance, so again, if I were moving, there'd be resistance, but this cat is at rest. So there's a support force. There's a surface that the cat is sitting on, and it's supporting it from falling. So the table pushing back won't count. You're right, Danny, but what do we call that? We're going to call that the normal force, actually. So normal force just means if there's it says, what did I write? I wrote the wrong thing. Did I write a support force due to friction? That's wrong. It should say a support force due to a surface. I'm sorry, that's my fault. No wonder we didn't get it because I wrote the wrong thing. So let me just change my video for a second. So change this definition. This should say, normal force should say a support force due to a surface. All right, so anyway, so what I'm going to do is, to cancel this out, I'm going to draw a normal force pointing up that's the same size as gravity. All right, so I'll go here, and I'm going to draw a normal force that points up. And it says make sure to include the net force, so I know the net force is 0, so the other thing that I'm going to include on my free body diagram is I'm going to say F net equals 0. So that's my free body diagram. Okay, the last question, if the cat's weight, and I wish I didn't write on that, but if the cat's weight is 90 newtons, what is the normal force acting on the cat? Well, so let's label, first of all, we were just told the weight or the force of gravity is 90 newtons. Question C says, if the gravity is 90 newtons and I'm at equilibrium, how much does the normal force need to be? So anyone can go ahead and share in the chat. If I want my net force to be 0 and I've got 90 going down, how much does the normal force need to be? Yes, Chloe. Yep, good. It needs to be 90 newtons. And yes, Danny, that's a good point. Technically, we should be saying it's 90 newtons up because it's got a direction as well. All right. That wasn't too bad. And hopefully now you at least see why we have those 6 types of forces. All right, so let's try a different one. A car is moving east along the interstate at a constant speed. First question, is this car at mechanical equilibrium, and how do you know? So anyone can go ahead and try and answer that. Anybody got an idea whether this is at equilibrium or not? It is moving forward, Max, so that's true. It is moving forward, so it's not at rest. But this is where I want to be clear, and it's been a couple days since we talked about equilibrium. There are 2 times that the net force is 0, at rest, or, remember the first law, every object, an object at rest stays at rest, or an object in motion stays in motion in a straight line. So I'm going to say yes to what Danny's saying here, right? It's a constant speed. So if it's a constant speed, we are actually going to say in this case, it is still a case of mechanical equilibrium. So is it in mechanical equilibrium? Yes. Why? Because it's a constant speed. So that makes us think then about something when we go ahead and draw a free body diagram. So when we draw our free body diagram, same thing. We're going to start with a dot. Pardon me. So we're going to start with a dot. I'm going to tell you in this case, we had 6 types of forces. There are 5 of them that are acting on this. So let's think. I'm on Earth and I'm not flying, which means that there's something holding me down. What would I call the force that's holding me down? Gravity, yes. So the car has gravity, but it's not falling because there's a road there. And if the road's holding us up, that's going to be normal, yes. It's still a surface holding me up. So those 2 should be equal so that they cancel each other out. Let me just do this a little bit differently. Okay. Then we've got the cars going forward. So this is where we're going to talk about the applied force. Remember we said an applied force is any generic push or pull. So the engine is what's pushing this car forward now. Pardon me. And so since the engine is pushing it forward, we're going to say that's an applied force pointing forward. There are 2 forces going backward. Anyone want to guess one of them? Why am I getting a phone call? I'm not going to answer right now. Yeah, friction is one of them. I'm going to friction going back. Because again, we wrote down that friction always opposes motion. So we're going to have friction, and yes, the other one, Max, is air drag. So we're going to call that FD. And you'll note I put them back to back. And I've drawn it so that approximately the size of this pair of vectors is the same as the size of the applied force. All right, so that's the free body diagram. The last thing we need, it says make sure to include the net force. So we're going to say here that the net force is 0 again. Okay. Last part of this problem. The car has an applied force of 700 newtons and a friction force of 300. So applied force is 700 newtons. The friction force is 300. What does drag have to be? Oh, sorry, Olivia. Glad to have you back. If you need to, in a bit, I'll post a video at the end. So if there's anything you missed, you can look back at it. All right, so anyone got an idea what drag will be in this case? So again, we're at mechanical equilibrium. Yep. I think it's 400, right? Because we need right and left to be equal. So if I've got right going 700, I need left going 700. There's 300 here. What's left for part C? The force of drag is going to be 400. All right. Let's try one more together, and then I'm going to have you try one, and then we'll be done. I'm going to go ahead and go to the next slide. So we're going to imagine the same car now. Oops, why is that? I don't know why that did it that way, but it's the same car, but now the car is accelerating forward. So if it's accelerating forward, am I in mechanical equilibrium? No, because the two types of mechanical equilibrium are constant speed or being at rest. So no, not at constant speed. So in this case, my free body diagram is going to be very similar, except if I'm not in mechanical equilibrium, I need one force to win. Which force needs to be the biggest force in my drawing? Yes. The applied force needs to be the biggest force in the drawing, because we need gravity and normal to cancel out, because I'm not going up or down, but I am accelerating forward, so I need a bigger applied force than either my friction or my drag. And the last thing I'm going to do here is we've only drawn things that have a net force of 0. Now that I know that the forward's winning, the way we're going to draw that is I draw it as a double arrow separate from the free body diagram to say that this is the net force, and the net force is pointing forward. Oops. All right. So it says the frictional and air resistance are the same as the last problem, but this time the car has an applied force of 900. So let's look back. In the last problem we had, oops, friction is 300, drag is 400. So let's add that to our picture. Okay, whoop. What am I doing wrong? Was it friction was 400, I think? Drag was 300. And now I'm saying that my applied force is 900. So what's my net force? Oh, did I do it backwards? Okay, sorry. I'll fix that real quick. Thanks, Chloe. Wait, so this one was what? This one was 300, 400. Okay. All right, so yeah, 900 minus 300 minus 400 should be a net force of 200 newtons. So that's my answer to part C, right? Net force is 200 newtons, right? I got any questions? The last thing I'd like to do before I let you go is I'd like you to try one. So I'm giving you one that has only 2 parts. So I'm giving you a little bit of an easier one. So go ahead and see what you can do with the free body diagram first. So everyone go ahead and just try this in your notes. I'll just give everyone a chance to do it and then we'll talk about it. First hint that I have is there are 2 forces on this. Danny, no. And Scott, yeah, that is the overall answer. But no, so what's happening here is if you're lifting the bucket with a rope, right? So I'm just gonna, you don't necessarily need to draw this picture, but if I want to just kind of talk about it, right? If I'm lifting a bucket with a rope, the rope is pulling the bucket up, right? Yeah, yep. So in this case, I've got that up force. What do you think we're gonna call it if it's a rope? You could call it applied. I would accept applied, but since it's a rope, I would call it tension. So I'm going to have tension going up, and I want to be clear, it's not normal going up because it's not a surface. So Kylie, tension going up, and then there should be gravity going down, but who's winning? I'm going up. Tension better win. All right, and it's saying gravity's 23. It's saying that tension is 45. So I know that my net force is going up. By how much? I think Scott had that a second ago. Wait, are we sure it's 12? Do your math one more time, I think, Scott. Yeah, I think it's 22. I think you forgot to carry a 1 or something, Scott. But yeah. All right. I know I said that was the last one, but that was too easy. So we'll do one more, but I only have one more, so I can't give you one more after this. But any questions about 4? All right, here's the last one. Oh no, this one's more complicated. Dang it. You know what? I don't have time for this. Sorry, we'll stop at 4. I would like you guys, if you don't mind, in today's folder. So let me go back here. Because I want to see how you're drawing these. Can you see that? No, you can't. Yeah, you can. All right. So I want to see how you're drawing these so that I know what I need to teach. Because sometimes sometimes the things that you think are important to draw aren't the same things that I think are important to draw. So I just want to see how everyone's doing on this. So if you would, before you leave for the day, just take a picture of your notes, what you did with your notes. You can use Cam Scanner or Genius Scan, or you can just use your regular camera. I'm fine with whatever. But in today's folder, there's a place for Newton number 2 practice. If you would do me a favor and just upload that before you leave, I would appreciate that. I'll just put a quick participation and grade in for that. But mostly I'm just interested in seeing how you guys are drawing it and if it's the same way I'm drawing it. Before you leave, let me double check attendance. Did Camille end up in here? Yes, she did. I thought I saw her. Okay, Shelby, are you in here? I don't see Shelby. Aiden, are you in here? No. Grant? Noah? Ivana? Rowan, I saw you came. Sam? Sam Shockley, are you in here? All right, so currently I have absences as Shelby, Aiden, Grant, Ivana, Sam. If I accidentally, if any of you are here, make sure you tell me. Once you guys, once you submit your picture, you are free, and have a good weekend. I miss you guys. This is much weirder, but see you later.